Welcome back to the Deep Dive. Today, we are taking a fascinating shortcut right into the kitchen, the lab, even the wilderness, really,
Mm-hmm.
to understand the fundamental chemistry that dictates, whether something tastes sour or bitter or salty.
Exactly. We're talking about acids, bases, and salts.
That's right.
And this is really the hidden chemistry of everyday life. We're going to unpack the fundamentals of flavor, reaction, and even survival, starting with, well, maybe the most relatable experience, that feeling of eating way too much.
Right, that awful acidity. So let's jump straight into a practical hook question then. If you have that serious acidity, that painful burning feeling after a big meal, what should you reach for? Lemon juice, vinegar, or maybe baking soda dissolved in water.
Definitely the baking soda solution, 100%.
Okay, why is that?
Well, the reason you need that specific one is because of this chemical balancing act we call neutralization. You see, acidity means there's excess acid in your stomach. And baking soda, well, it's a mild base. It's not corrosive or anything. So it acts like a chemical peacekeeper, basically. It goes in and nullifies that aggressive acid, bringing pretty immediate relief.
A peacekeeper. I like that. So our mission today is to sort of uncover these simple but really powerful concepts and show you the incredible utility. I mean, from industrial chemistry all the way to nature's own defense mechanisms, that comes from just mastering these three simple ideas.
Absolutely.
Okay, let's unpack this. Where do we start? How about identifying them safely?
Good place to start. You're right. In the kitchen, we taste things. Sour usually means acid. Bitter often means base. But in a lab, tasting is a huge no-no. It's dangerous.
Definitely.
So we rely on these chemical spies, you could call them, known as indicators. They change color instantly when the environment around them shifts from acidic to basic or vice versa.
And the classic spy everyone remembers from school is probably litmus paper.
It is, yeah. Litmus is actually a purple dye. It's extracted from lichen, which is this really fascinating hybrid organism, part fungus, part algae.
Huh, interesting.
And it's simple. If you dip blue litmus paper into an acid, it turns red. If you dip red litmus paper into a base, it turns blue. It's a beautifully simple and all-natural detector.
But I think the indicator hiding right in our spice racks is maybe even more fun. Turmeric.
Ah, yes. The famous curry stain test. Think about it. You get that bright yellow curry on a white shirt.
Happens all the time.
Right. And when you scrub it with soap, and soap is always basic, what happens almost instantly.
It turns reddish brown.
Exactly. That immediate color shift confirms the base is present. Then, when you rinse it with loads of plain water, the yellow color usually comes back. Turmeric is just a phenomenal, really sensitive household indicator.
Okay, but here's where it gets, for me, really interesting. Because not all indicators rely on color, do they? Some use smell, these olfactory indicators.
That's right. That's a great point. These substances, they actually change their odor when they're exposed to an acid or a base. The source material mentions things we have at home, like finely chopped onion or vanilla essence, even clove oil.
So how would you test that? You take, say, some chopped onion.
Yeah, and you'd test its smell with dilute hydrochloric acid, and then maybe with a base like sodium hydroxide solution. And you'd find that its characteristic smell either changes quite dramatically, or it might even disappear completely, depending on whether it's in the acid or the base. It's like chemical detection, but for your nose.
Pretty neat.
Which actually pivots perfectly into our next section, the action. What happens when we actually mix these substances? Let's kick things off with a really foundational reaction, one that's used a lot in industry, but it has a slightly dangerous edge. Acids reacting with metals.
Okay, so the basic formula here is acid plus metal gives you a salt plus hydrogen gas. Is that right?
That's the general rule, yes. A good example is if we drop small zinc granules into some dilute sulfuric acid.
Okay.
The zinc basically pushes the hydrogen out of the acid, it displaces it, and you start seeing bubbles forming. That's pure hydrogen gas being released.
And hydrogen gas is flammable, right?
Right.
So how do we prove it's actually hydrogen?
Ah, the classic pop test. You need to collect the gas first, maybe by bubbling it through some soap solution to make nice gas-filled bubbles.
Right.
Then you carefully bring a burning candle or a lit splint near one of those bubbles, and what do you hear?
A little explosion. That distinctive pop sound.
Exactly. That sharp pop sound confirms that highly flammable hydrogen gas is present. It's quite dramatic.
Okay, so that's explosive. Let's contrast that with maybe a more common or helpful reaction. Acids reacting with metal carbonates or hydrogen carbonates, the foaming one.
Yes, the fizzing. Like when you mix baking soda, which is sodium hydrogen carbonate, with an acid like vinegar.
Yeah, you get loads of bubbles, like a volcano experiment.
Precisely. That reaction produces three things: a salt, water, and that fizzing gas, which is carbon dioxide, methane CO2
And there's a test for methane CO2 as well, isn't there?
There is another classic test. If you bubble the gas that's produced through lime water, that's a calcium hydroxide solution, the clear lime water turns milky white.
And what's actually causing that milkiness?
It's the formation of calcium carbonate, mathrm carclo-33. And what's fascinating, as you pointed out, is that this calcium carbonate is the exact same chemical compound that makes up things like chalk, limestone, and even marble.
Wow. So that simple gas test connects to massive geological formations.
It does, which brings us neatly back to that ultimate balancing act we started with, neutralization.
Right. The acid meets the base, they cancel each other out, and you're left with just salt and water.
Exactly. And we can see this very vividly in the lab. Imagine you have a basic solution, say sodium hydroxide, and you add a couple of drops of an indicator like phenolphthalein. The solution turns this bright pink color.
Okay.
Now, as you carefully add an acid, drop by drop, suddenly the pink color vanishes. Poof, gone. You've neutralized the base.
Wow.
But here's the cool part. If you maybe add one drop too many of the base again, that pink color snaps right back. It shows that the neutralization is completely reversible. It's a very precise balance.
That makes sense. But, thinking about other compounds, like oxides, why do metallic oxides, like copper oxide, act like bases? They don't have that hydroxide, that OH group we usually associate with bases.
That's a really good question. It's all about how they react. When metallic oxides react with an acid, they behave chemically just like a base where they produce a salt and water.
I see.
So, for instance, if you take copper oxide, which is a black powder, and react it with dilute hydrochloric acid, the solution turns this beautiful, very distinctive blue-green color. That color comes from the copper salt that's formed, copper 2 chloride. Because it reacts this way, we classify metallic oxides as being basic oxides.
Okay, so if metallic oxides are basic, then non-metallic oxides must be.
Acidic, precisely. And that makes sense with what we saw earlier, right? Carbon dioxide, mathrm CO2 is a non-metallic oxide, and it reacted readily with the basic lime water in that milky white test. That confirms its acidic nature.
Right, it all fits together. So that sets the stage for our next section. If, as we said, not everything containing hydrogen is an acid like glucose or alcohol, don't act like acids. What is it? What specific property gives acids and bases their defining chemical character? Is it just about the hydrogen?
It's a bit more specific than just having hydrogen. The key test here is electrical conductivity. See, acids like hydrochloric acid or sulfuric acid only really show their acidic properties when they're dissolved in water.
Okay.
And in solution, they conduct electricity. Why? Because they release mobile charged particles. Specifically, acids release hydrogen ions, Ca++ plus +La, which are positive ions, or cations. These ions can move and carry an electrical current, which is why a bulb in the circuit would light up.
Ah, okay. So the mathrm H plus sonolars is the real signature of an acid in water.
Yes, but there's a slight subtlety. Mathrm H plus ionos are actually incredibly reactive. They can't really exist on their own in water for long. They immediately latch onto a water molecule, mathrm H2 mathrm, to form what's called the hydronium ion, mathrm H3 mathrm plus. So technically, it's the hydronium ion concentration we're looking at. But the critical takeaway is water is essential. Acidic properties only show up when water is present to allow these ions to form and separate.
So dry mathrm HTL gas, for example, wouldn't turn litmus red.
Exactly. Dry mathrm HTL gas doesn't act like an acid because there are no free ions.
Fascinating. And for bases, what's the equivalent ion?
For bases dissolved in water, the characteristic ion they generate is the hydroxide ion, mathrm OH. And bases that are soluble in water, they get a special name. We call them alkalis.
Okay, alkalis. Now, speaking of dissolving things in water, we absolutely have to pause for that crucial safety point about dilution. This sounds really important.
Oh, it is. This is non-negotiable safety advice. The process of mixing a concentrated acid or a concentrated base with water is highly exothermic.
Meaning it releases a lot of heat.
A massive amount of heat very quickly. So the rule is you always add the acid or base slowly to the water while stirring constantly. Never, ever the other way around.
Why not? What happens if you add water to acid?
If you add water to concentrated acid, the heat generated is so intense and so immediate that it can actually boil the small amount of water you just added, turning it into steam explosively, and that can splash the concentrated corrosive acid everywhere. It's incredibly dangerous.
Wow. Okay, message received. Always add acid to water, slowly, with stirring. A to W.
A to W, exactly. Remember that.
Got it. So once we have these solutions safely prepared, whether they're strong or weak, we need some way to measure just how acidic or basic they are, like a ruler for acidity.
And we have one. That's where the pH scale comes in.
Ah, pH. I've heard of that.
The pH actually comes from the German word Potenz, meaning power. So the pH scale measures the power of hydrogen, or more accurately, the concentration of those hydrogen or hydronium ions.
And how does the scale work?
It typically runs from 0 up to 14. A pH of 0 is extremely acidic. A pH of 14 is extremely basic, or alkaline. And right in the middle, a pH of 7 is considered perfectly neutral, like pure water.
Okay, 0 to 14, 7 is neutral.
Yeah.
And what's the core relationship between the ion concentration and the pH number?
It's an inverse relationship, which sometimes trips people up. The higher the concentration of those acidic hydronium ions, +1 the most plus, the lower the actual pH number.
Lower means more acidic.
Exactly. So a strong acid like hydrochloric acid produces lots and lots of xanthan H plus ioners when dissolved, so it has a very low pH, maybe 1 or even 0. A weak acid, like acetic acid in vinegar, produces far fewer xanthan H plus ioners, so its pH is higher, maybe around 3 or 4, closer to neutral.
Okay, that makes sense. And this isn't just some abstract chemistry concept, is it? pH seems to be literally the difference between, well, a helping environment and a crisis. Let's look at pH in everyday life.
Absolutely. It's everywhere. Think environmentally first. Most living organisms, including us, are incredibly sensitive to pH. We generally only survive within a very narrow pH range, roughly 7.0 to 7.8.
That narrow.
Yes. So when you get acid rain, which is defined as rain, with a pH below 5.6 falling into rivers and lakes, it lowers the water's pH. And if it drops too low, aquatic life just can't survive. It disrupts their entire ecosystem.
And you mentioned Venus earlier.
Right. As an extreme example, the atmosphere of Venus is literally cloaked in thick clouds of sulfuric acid. The pH there is incredibly low, making it an environment where life as we know it just seems impossible. Too harsh.
Okay, let's bring it closer to home.
Mhm.
What about inside our own bodies? Our digestive system, for instance. Our stomach produces acid, right?
It does. Our stomach naturally produces hydrochloric acid, Mothram HTL, which is essential for digesting food and killing harmful bacteria.
But
Sometimes, especially during indigestion, the stomach produces too much acid, and that excess acid causes that familiar, painful, burning sensation.
So what's the fix?
Antacids. We take a dose of a mild base. A very common one is magnesium hydroxide, which you might know as milk of magnesia. This base neutralizes the excess stomach acid, relieving the pain and restoring the proper balance.
Ah, neutralization again. And what about the pH battle happening maybe right now in our mouths?
Yes, oral hygiene. Tooth decay actually starts when the pH in your mouth drops below 5.5.
Why does it drop?
Bacteria in our mouths feed on leftover sugars from food and drinks, and as they metabolize these sugars, they produce acids as a waste product. It's this acid that attacks our tooth enamel.
Enamel is tough, though, isn't it?
It is. Tooth enamel, which is mostly calcium hydroxyapatite, is the hardest substance in the human body. But even enamel starts to corrode and dissolve when the pH gets below 5.5 for extended periods.
So acid is the enemy here.
Acid is the enemy, and the solution. Since acid causes the problem, we use basic toothpastes. They help neutralize the acids produced by bacteria, raising the pH back above that critical 5.5 level and stopping the decay process before it can really start. Simple, but effective. Now, my favorite example you mentioned earlier, nature's own chemical warfare.
Haha, yes. Think about a honeybee sting. When a bee stings you, it injects an acidic substance, which causes that immediate sharp pain and swelling.
Right.
So what's a common home remedy? Applying a paste of baking soda, a mild base, to the sting site. The base neutralizes the bee's acid, providing some relief.
And the stinging metal.
Same principle.
Okay.
Those stinging hairs on a nettle leaf inject methanoic acid when they touch your skin, causing that characteristic burning rash. And traditionally, what's the remedy people look for?
Isn't there usually a dock leaf nearby?
Exactly. People rub the crushed leaf of the dock plant on the nettle sting, and it often works because the dock leaf contains basic compounds that neutralize the nettle's methanoic acid. Nature provides the sting and, conveniently, sometimes the antidote right next to it. That's incredible. Nature's own little neutralization toolkit growing side by side. Okay, moving on from defense mechanisms, let's talk more about the products of neutralization, salts. And we have to start with the most important salt of all, sodium chloride, common table salt.
Mycel. It's truly a foundation stone, not just for chemistry, but for history and civilization too. It's either harvested by evaporating seawater or mined from underground deposits as rock salt, which often looks brown because of impurities.
And its importance can't be overstated, can it? Thinking historically.
Absolutely. The sheer importance of salt for preserving food, for bodily functions, and for commerce is why Mahatma Gandhi's famous Dandi March, the Salt March, was such a powerful symbol in India's struggle for independence. It highlighted the essential value of this simple compound.
And beyond its direct use, common salt is also the starting material, the raw ingredient for a whole range of really powerful household and industrial chemicals, like the chlor-alkali process. What's that about?
It's quite amazing, actually. The chlor-alkali process involves taking a concentrated solution of common salt, which we call brine, and passing an electric current through it. Electrolysis.
Okay.
And this process splits the brine into 3 completely separate, incredibly useful industrial products all at once.
3 from 1. What are they?
You get sodium hydroxide, mathrin NaOH, which is a strong base, and alkali, used heavily in making soap, paper, and textiles. You get chlorine gas, Mathrm Ki-Il-2, which is used for water purification, leach, and making plastics like PVC. And you get hydrogen gas, Mathrm HO2, used as a fuel and in making ammonia for fertilizers.
Wow. One simple starting ingredient, brine, gives rise to 3 industrial pillars. That's efficient.
Very efficient.
The source material also detailed 2 other really essential salts derived from sodium chloride, baking soda and washing soda. We've mentioned baking soda already.
Yes, baking soda, or sodium hydrogen carbonate, HCO33. It's that mild, non-corrosive base we use in antacids, but also crucially in cooking.
For making things rise.
Exactly. When you heat baking soda, like when you're cooking crispy pakoras or making a soft cake or bread, it releases carbon dioxide gas. Those gas bubbles get trapped in the batter or dough, making it expand and become light, soft, and spongy.
Right. And its bigger sister, washing soda. What's the difference?
Washing soda is sodium carbonate, Mathrm NO2, Mathrm CO33. It's a stronger base than baking soda. It's really critical for industries making glass, soap, and paper. And as the name suggests, it's famously used as a powerful cleaning agent in detergents. It also has another important household use,
Which is?
removing the permanent hardness of water. Hard water contains dissolved calcium and magnesium salts that prevent soap from lathering properly. Washing soda reacts with these salts and removes them, softening the water.
Ah, that's why it helps with laundry. Now, when we look at the chemical formula for washing soda, it often has this curious extra bit written on the end. Mathrm Ki-O3, what does that .10H2O signify? Are the crystals actually wet?
That's a great observation. And it leads us to our final surprise, the concept of water of crystallization. Many salts, when they form solid crystals, incorporate a fixed number of water molecules right into their crystal structure.
But they look dry.
They look and feel perfectly dry, but the water is chemically bound within the lattice. Think of copper sulfate, Mathrm CuSO4. It's famous for its beautiful bright blue crystals. That blue color is due to the presence of 5 water molecules per formula unit, written as Mathrm CuSO4 half-palled 5NSO4.
Okay, so what happens if you remove the water?
If you gently heat those blue crystals, the water of crystallization is driven off as steam, and what you're left with is anhydrous copper sulfate, which is a stark white powder.
Wait, from blue?
Yes, but here's the magic trick. If you add just a drop or 2 of water back to that white powder,
Does it turn blue again?
instantly, the beautiful blue color is restored as the water molecules re-enter the crystal structure. It's a really visual demonstration of this bound water.
That's pretty cool. And this concept, water of crystallization, is the key to how plaster of Paris, or PAPI, works, isn't it?
It is, exactly. We start with gypsum, which is calcium sulfate dihydrate, Mathrm H2, Mathrm has 2 water molecules.
Right.
If you carefully heat gypsum to a specific temperature, around 373 Kelvin or 100 degrees Celsius, it loses about 3/4 of its water of crystallization. It forms calcium sulfate hemihydrate, hemi meaning half Mathrm CaSO4, frac 1,2 Mathrm HOO, that is plaster of Paris.
Half a water molecule. How does that work?
It's actually 2 formula units of Mathrm and CaSO4 sharing 1 molecule of water between them, but we write it as hemihydrate for simplicity.
Okay. And why do doctors use this white PAPI powder?
Because when you mix pot powder with the right amount of water, it rapidly absorbs the water, reforms gypsum crystals, and sets into a hard, solid mass within minutes. This property makes it perfect for creating casts to support fractured bones and keep them immobile while they heal. It reverts back to the hard gypsum state.
What a fantastic journey. Seriously. We started with something as simple as a painful stomachache, and we've ended up talking about life-saving medical casts, revolutionary moments in history, industrial chemical production. It's truly amazing how this simple interaction, this balance between hydrogen ions and hydroxide ions, underpins so much of our daily lives and the world around us.
It really does. We've seen that whether a substance conducts electricity or tastes sour or brings relief from an insect bite or is used to make soap or fuel or glass, it all comes down to the concentration and activity of those key ions, methylmase plus and methylmase. Understanding acids, bases, salts, and the pH scale is in many ways understanding the health and vitality of our environment, our industries, and even our own bodies.
Absolutely. So we'll leave you, our listeners, with this final thought to mull over. We know our bodies, especially our lungs, function best within that very narrow, tightly regulated pH range, around 7.0 to 7.8. Now, if the air we breathe, particularly in polluted areas, at a constant, maybe low level but persistent, concentration of acidic non-metallic oxides from traffic fumes, from industry, what long-term, maybe subtle changes might that impose on the delicate pH balance in the fluid lining of our lungs? And what unseen, continuous biological defense mechanisms must be working, second by second, inside us, constantly trying to neutralize that incoming acidic threat just from the air we breathe.
That's a deep one to ponder.
It is. Something to think about. We'll leave you with that until the next Deep Dive.